For over 2,000 years, human understanding of matter hit a dead end at a concept the ancient Greeks called atomos. It translates to uncuttable, the idea that if you divide a material down far enough, you eventually hit a fundamental, impenetrable building block of reality. In the early 19th century, John Dalton adapted this ancient philosophy into a working scientific theory. He defined matter as a collection of microscopic, perfectly solid, indivisible spheres. Dalton's work organized the chaos, giving scientists a sense of certainty that the basic structural unit of the universe was finally solved. But the model couldn't account for everything. If atoms are just uniform, solid rocks, they offer no mechanism to explain why rubbing a glass rod creates static electricity, or why certain gases emit a distinct glow when heated. The tidy universe of classical physics was an illusion. The invention of high-voltage vacuums was about to expose the first crack in that solid sphere. J.J. Thomson, an English physicist, began running electricity through specialized vacuum tubes to investigate these anomalies. Inside this strange apparatus, known as a cathode ray tube, Thomson observed a glowing beam of particles. By applying magnetic and electric fields to the tube, Thomson could bend the beam. He balanced the opposing forces to calculate the mass and charge of the particles inside, realizing they were not atoms at all. They were negatively charged pieces smaller than atoms. He had discovered the electron. Shortly after, American physicist Robert Millikan designed an experiment to measure exactly what Thomson had found. Millikan sprayed tiny drops of oil into a chamber, zapped them with a negative charge, and used an electrical field to counteract gravity. He perfectly suspended them in midair. By running the math on the balanced forces, he isolated the exact minute charge of a single electron. Meanwhile, Eugen Goldstein was running similar vacuum experiments and found evidence of particles moving in the opposite direction, discovering a positive counterpart we now know as the proton. The atom was broken. Dalton's solid block was replaced by Thomson's plum pudding model, a soft, positively charged matrix with negative electrons dotted throughout it, like fruit in a cake. Ernest Rutherford decided to test the structural integrity of this new plum pudding model. He set up a radioactive source to fire a beam of heavy, positively charged alpha particles directly at an incredibly thin sheet of gold foil. According to classical physics, if the atom is a soft, diffuse matrix of charge, those heavy, fast-moving alpha particles should punch straight through the foil like bullets through tissue paper. Most of them did, but an anomaly appeared. A small fraction of the particles violently deflected, with some ricocheting almost straight back toward the emitter. Rutherford realized that the atom is almost entirely empty space, anchored in the center by a microscopic, staggeringly dense, positively charged nucleus. But Rutherford's model had a fatal flaw. Classical physics dictates that an orbiting electrical charge must constantly radiate energy. If an electron behaves like a tiny planet, it should lose momentum, spiral inward, and collapse into the center in a fraction of a second. Physicists were wrestling with an anomaly called black-body radiation. Classical math failed to explain how objects absorb heat and emit light at varying temperatures. If classical mechanics were true, every atom would immediately collapse, and everyday objects would emit infinite radiation. The old rules had reached their limit. Niels Bohr resolved this crisis by abandoning the classical rules of reality. He focused on one specific piece of evidence. When you excite hydrogen gas with electricity, it doesn't emit a smooth, continuous rainbow. It emits sharp, distinct lines of specific colors, like a glowing barcode. This illustration shows Bohr's solution. He proposed that electrons do not orbit freely. Instead, they are locked into distinct, fixed energy shells circling the nucleus. Looking at this curved energy level diagram, an electron only jumps to a higher state if it absorbs the exact energy to cross the gap. Falling back down, it releases that energy as specific wavelengths. Those downward drops create the barcodes of color. This table outlines the Rydberg formula, which perfectly predicted the exact wavelengths of light emitted by hydrogen, providing mathematical proof for the shell model. Bohr's model proved that energy and matter at the lowest level do not operate on a smooth, continuous spectrum. They exist as a strict staircase of distinct, quantized steps. In just over a century, the solid sphere was cracked open, filled with charges, hollowed out by a nucleus, and finally restrained by the rigid mathematics of quantum mechanics. This evolution was driven by a community of physicists who prioritized experimental anomalies over established theories. Scientific progress is built on the willingness to dismantle established models of reality the moment the universe reveals a contradiction.